Hello everyone, let's design DisJointSet with QuickUnion. Then we further optimize QuickUnion using path compression and union by rank. This is going to be very interesting one. Please watch till the end. Before moving on to that, let's understand why we need DisJointSet. For example, you have two graphs. One graph has vertices as 0, 1, 3, 5. Other graph has vertices 6, 7, 8. How do you know that two vertices are connected? Let's see here, is vertex 3, 5 are connected? Yes, because they are sharing common parent. Is vertex 7, 8 are connected? Yes, because they are sharing common root. Similarly, is vertex 5, 6 are connected? Obviously not, because they are not sharing either common parent or common root. Then, if you are having infinite number of vertices in a graph, how do you know that they are connected? The solution is disjoint set. Disjoint set provides very good efficient algorithms through which we can easily determine two vertices are connected or not. Quick union is one of the reliable algorithm with disjoint set. The disjoint set provides two operations. One is union, it joins two vertices. Another one is find, it returns parent or root of a vertex. Let's design a disjoint set with quick union. Assume you have vertices of size 5 starting from 0, 1, 2, 3, 4. In quick union, we are going to take root array, where the size of the root array is equivalent to number of vertices present in a graph. Here, the number of vertices are 5, so that root array size is going to be 5. And each index of a root array represents a vertex present in a graph. The value of a index is equal to root vertex. That's it. So initially every vertex is independent so that the root of every vertex remains same. It means the value of each index is equal to index. So index 0 or vertex 0 value will be 0. Index 1 or vertex 1 value will be 1. Similarly for 2, 3, 4. Let's make a connection between vertex 0, comma 1. So we call it as union of 0, comma 1. Now we consider first vertex as a root vertex. Here vertex 0 is going to be the root. So let's move. Vertex 0 will be represented by index 0. Let's move on. Index 0 has value 0. How do you know that the given vertex is root? When the index and its value is equal, we call it as a root vertex. Here index 0 value 0, so that 0 is the root. So we replace value 0 with index 1, so that index 1 value becomes 0. We establish a connection between 0, 1. Now let's make a union between 1, 2, so that we consider vertex 1 as a root. Vertex 1 represented by index 1. Index 1 has value 0, so that index 1 is not the root. We move on to its parent, so that is index 0. Index 0 has value 0, so that index 0 or vertex 0 is going to be the root, so that we replace value 0 with index 2, so that index 2 value becomes 0. We establish a connection between 1, 2. Let's do union of 3, 4. We consider vertex 3 as the root, index 3 has value 3, so that 3 is the root, replace with index 4, 3, 4 are connected now. Let's see, is vertex 0, 2 are connected. Let's find root of 0, so that index 0 has value 0, so that the root is 0. Then find root of 2, so index 2 has value 0, so move on to index 2, 0. Index 0 has value 0, so that 0 is the root. Find out 2 also returns 0. So both the vertices sharing common root, so that they are connected. Now let's move on. Is vertex 3, 4 are connected? So find the root of index 3. So obviously which is 3. Find root of index 4. So that index 4 has value 3. So that move on to index 3. Index 3 has value 3. So that 3 is the root. So that find out 4 returns 3. So 3, 4 are connected. Now let's move on. Is vertex 1, 4 are connected? So find out 1. Obviously it returns 0, because then let's move on. Find out 4. So that find out 4 has index 4 has value 3. So move on to index 3. Index 3 has value 3. So 3 is the root. Find out 4 returns 3. So now both the vertices sharing different root, so that they are not connected. Now let's make a connection between 2, 3. So union of 2, 3, so that vertex 2 is going to be the root. So that index 2 you have value 0. So we move on to index 0. Index 0 you have value 0, so that 0 is the root, so that replace value 0 with index 3, so that index 3 value becomes 0. Now 2, 3 are connected. Now let's see, is vertex 1, 4 are connected. So find of 1, move on to index 1, has value 0, move on to index 0, it has value 0, so that 0 is the root. Now find of 4, this is going to be interesting. Now you see at index 3 you have, at index 4 you have value 3, so that 4 is not the root, so that move on to index 3. At index 3 you have value 0, so that 3 is not the root, so that move on to index 0. Now at index 0 you have value 0, so that 0 is the root. Now find out 1 and find out 4 returns same root, so that they are connected. So this is how the quick union works. So let me walk through the code. So initially we will take a root array. The size of the root array will be initialized within a constructor. So the size is equivalent to number of vertices size, and initially every vertex is independent, so that root array of index is equal to index. Now the find method is going to return the root, right? So that find of index, if index not equal to its value, so we just move on to its parent. Finally we will just return the root index. Then the union method takes x, y vertices. So root x is going to be find of x, root y is going to be find of y. If root x not equal to root y, we just replace root array of root y equal to root x. That's it. Let's see the time complexity here. The find method, if it is a screwed graph, so it will end up moving on to all the indexes, so that the time complexity will be linear. And the union method purely depends on find method, so that time complexity again be linear. Can we improve this? Yes, we can do that with path compression. Let's see how can we do that. Assume you have a screwed graph, so where the vertices connected in a screw manner. So let's make a union of 3, 4. So obviously we consider vertex 3 is going to be the root. So here the height of a graph is going to be 4. So we need to compress this path. How do we do that? So initially we take a stack. Now the stack is empty. So we consider vertex 3 as a root, right? So that vertex 3 has parent 2. So that vertex 3 is not the root. So that first we copy 3 to the stack. Then vertex 2 has parent 2, parent 1. So that vertex 2 is not the root. So that we copy 2 to the stack. Now vertex 1 has the parent 0, so that vertex 1 is not the root, so that we copy vertex 1 to the stack. Now see here, vertex 0 doesn't have any parent, so that vertex 0 is the root. So now what we do, we got root as 0, so we just pop the elements from the stack. We assign for each element present in stack root as 0. So as a first element in the stack you have 1, so that 1 root is going to be 0, which is already 0. And second element in the stack is 2, so that 2 root is going to be the 0. Then third element from the stack is 3, so that 3 root is going to be the 0. Now union of 3, 4, so we consider vertex 3 as a root, right? So 3 root is 0, so that obviously 4 root also going to be 0. This is how we compress the path. Now let's see, is vertex 1, 4 are connected. So find of 1 obviously return 0. Find of 4 obviously return 0. So they are connected. So with path compression, we can make the time complexity of find method approximately log n. In best case, it is going to be constant. In average case, it is going to be log n. And we can also apply one more technique, which is union by rank. Let's suppose you have two disjoint sets. So one is 0, 1, 2, 5. One graph has two vertices 6, 7. So the first disjoint set having 0 as the root, second disjoint set has 6 as a root. See the rank of first disjoint set. Rank is nothing but you take up the maximum height, number of vertices are connected, we call it as a rank. So in disjoint set the rank is 3, in disjoint set 2 the rank is 2. Now we want to perform union between 0, 6. It means we want to connect two graphs. Let's consider 0 as the root. If you consider 0 as the root, so now 6 root is going to be 0. Now you see the rank of the graph, so which remains same, which is 3. For example, if you consider 6 as root, now 6 is going to be the root for vertex 0, so that now if you see the rank, so the rank will be incremented by 1. It means the height will be incremented by 1, so the rank is going to be 4. So this is not the recommended way of connecting graphs. So that whenever you are connecting a graph, maintain a rank, whichever root is having highest rank, make that root as a parent of other graphs, so that the height will remains same. So that's how we apply union by rank. So let me walk through the complete code. So here we take a root array and rank array. So obviously we initialize them within a constructor. So the size is equivalent to vertex size. So initially every vertex is independent, so that root of index is equal to index and rank of index will be 1. That's it. Let's move on to find method. Here we apply the path compression. So we take the index, it is nothing but vertex. You initialize a stack. If the index and its value not equal, then we push the index to the stack and we move on to its parent. Then we iterate from the stack until it becomes empty. So we just reassign root of stack.pop equal to index. So finally the index is going to be the root. That's it. So that's how we apply path compression. So let me walk through the union method. So you have x comma y, root x equal to find of x, root y is equal to find of y. Both the roots not equal, then we see rank of root y less than rank of root x, then root of root y equal to root x. If rank of root x less than rank of root y, then root of root x equal to root y. Else both are equal, so this we simply root of root y equal root x, we increment the rank of root x. That's it. So let's see the time complexity here. The find method, right? So as we are applying path compression, so on an average it is going to be log n, but the best case it is going to be constant. The union method purely depends on find, so that the time complexity in best case it is going to be constant, on an average it is going to be log n. That's it. So this is going to be very important code, so that please take a look on this code. You can find the complete code on my GitHub, link available in the description. So thanks for watching. My name is Srinu. I see you next time.